Hello and welcome back to the Quantum Information Reading Seminar, where our goal has been to read and understand the paper Black Holes as Mirrors by Hayden and Preskill. Today, in the last episode of this series, we are going to look at the final section of the paper entitled Are Black Holes Quantum Cloners? And then shortly conclude. Now, during the past weeks, as we've been reading through this paper, perhaps the suspicion has been growing in your mind that a black hole somehow, according to the assumptions of this paper, may be allowed or assumed even to be able to carry out a cloning of the infalling quantum data. So here I have a rough space-time diagram of the scenario that's envisaged in this paper. Alice throws in some information, in it falls, the black hole radiates the information out, Bob collects the information and is able to reconstruct the state that Alice threw in. If we call the state in this picture here, Alice throws in the state psi, and from the outcoming radiation from the black hole, Bob is able to reconstruct psi. Now, according to the assumptions of this paper, this conclusion has been justified, but there are of course a host of relativistic considerations that come along with this particular analysis, and in particular the authors themselves acknowledge that time dilation and other relativistic effects there is some tension between time dilation and other relativistic effects and the actual physical result, namely that Bob is able to reconstruct Alice's state. And the tension is that, and this is the tension that's addressed in this section today, the tension is that it's possible, according to the assumptions of this paper, that the state psi is simultaneously encoded in the internal degrees of the black hole, and also that Bob has reconstructed psi. And that there exists a time slice where this situation or state of affairs could be true, right? Because the state goes into the black hole, then some information leaks out of the black hole, and then Bob is able to very rapidly reconstruct this state psi. And if the dynamics of the internal degrees of freedom of the black hole are such that they move slowly enough and the radiation comes out fast enough, then there could exist this paradoxical situation where the state, Alice's a priori completely arbitrary state, coexists in the interior of the black hole and also in the exterior of the black hole. And that such a situation is forbidden by the laws of quantum mechanics thanks to the no cloning theorem, right? This would be a violation of the no cloning theorem in its strongest form of quantum mechanics. So the no cloning theorem tells us that there does not exist a universal cloning machine U, which is assumed unitary, which can take an arbitrary state, and it's important that this is true for all, or at least some class of states, psi, and some ancillary state, and take it to two copies of that state. There does not exist a unitary process, and indeed this theorem has been generalized massively over the intervening years. There doesn't even exist a physical process from within quantum mechanics that would allow you to clone an arbitrary quantum state in a fashion analogous to what I've just drawn here. This does not exist. There does not exist such a unitary, and this result is fundamental and incontrovertible. You can't get around this result if you assume the axioms of quantum mechanics. And so the scenario that Hayden and Preskill paint in their paper looks like it might, and this is the analysis we're going to discuss today, potentially allow for a violation of this theorem. And today we're going to discuss this whether or not this is likely within the assumptions that Hayden and Preskill have taken on in this paper, whether or not that's indeed justified, and therefore is it justified to make these assumptions, and finally, and most fascinatingly, is whether or not we should really allow for extensions or alterations of the laws of quantum mechanics to accommodate potential in-principle cloning. So let's continue reading through the paper, commencing at section 6. Are black holes quantum cloners? Our analysis has been premised on the assumption that black hole evaporation respects unitarity, and we've adopted the black hole complementarity viewpoint to describe the process. We have been led to the conclusion that a black hole whose evaporation is past the halfway point is really a sort of information mirror that quickly returns quantum information it receives. Now we should reassess whether our assumptions are consistent. We note that the geometry of the evaporating black hole contains space-like surfaces that are crossed by Alice's infalling quantum memory inside the event horizon and by the outgoing Hawking radiation that Bob decodes the outside horizon. So there's the Hawking radiation is outside the horizon, Alice's infalling quantum memory is inside the horizon. Therefore, if Bob can decode successfully, then Alice's quantum information has been cloned in the outgoing radiation. But cloning of arbitrary quantum states is inconsistent with the linearity of quantum mechanics. So this is a no-go, right? You cannot clone an unknown quantum state, an arbitrary unknown quantum state. You can clone, by the way, I mean, of course, this is something that should be obvious. It is possible to clone orthogonal states. Orthogonal states from a known set. So for example, if you only allow the states 0 or 1 to be processed by a potential cloning device, then of course there exists a device which can clone either 0 or 1. That's absolutely allowed by the laws of quantum mechanics, and such a gate is furnished by the C0 gate. The problem is if you allow superpositions, then you can no longer carry out the same trick. But that's an aside. So we seem to be stuck with a difficult choice. Either Alice's information is not re-emitted, or the black hole is a quantum cloning machine. Either way, the foundations of quantum theory need revision. This appears to be a powerful argument in favor of information loss. The hypothesis of black hole complementarity was proposed as a way to avoid this quandary. One chooses not to be bothered by quantum cloning if it occurs where no one can ever find out. According to this philosophy, we may accept for now that Alice, if she falls into the black hole, and Bob, if he stays outside, have sharply contrasting descriptions of the same physical process. So we accept contrasting descriptions of the same physical process. Eventually, we hope to be able to reconcile Alice and Bob's contrasting viewpoints, but finding the more complete global description must be postponed until we acquire a deep understanding of quantum gravity. In the meantime, we are entitled to insist that Alice's and Bob's descriptions are both compatible with the standard principles of quantum mechanics. So perhaps a way to summarize black hole complementarity in this context is we're going to allow an extension of quantum mechanics where, according to Alice's laboratory, quantum mechanics is obeyed. According to Bob's laboratory, quantum mechanics is obeyed, according to every observation that both observers can make. But we do allow for violations of quantum mechanics according to the global super laboratory that contains Alice and Bob. And this is a fascinating idea, right? So this is the space of Alice's observations, all the things that Alice, all the operation, this is meant to be a Venn diagram. So Alice's lab, all the operations that Alice could in principle carry out. And here's Bob's space of operations. And it turns out that you can easily conceive of situations where one observer can carry out a bunch of different measurements and another observer can carry out a bunch of different measurements, but neither of them can simulate each other, right? Because they're causally disconnected at some point. And that happens very much is almost generic in expanding space-time scenarios, right? You become causally disconnected at some point in an accelerating universe. And that means it's not even possible in principle for a local laboratory or observer to simulate the actions or effects of another local laboratory. So quantum mechanics is obeyed. We insist on quantum mechanics being obeyed here, but that in this hypothetical super observer who is able to simulate both Alice and Bob, a hypothetical super observer, we could allow for violations of quantum mechanics if which would be apparent to a hypothetical super observer able to simulate both Alice's operations and Bob's operations. Now, in spacetimes where causal connections are broken, such as when someone falls in a black hole or in an expanding universe, such super observers aren't allowed to exist. We don't admit them as possible. As an operationally existing entity. So why not, right? We can let's let there be a super observer who can sense violations of quantum mechanics. As long as quantum mechanics is never, a violation of quantum mechanics is never observed by Alice or Bob, then that should be fine. And the reason I find this extremely fascinating is that there has been recently a extraordinary consideration of extensions of quantum mechanics which are operationally meaningful, allow for quantum mechanics, it preserves some features of quantum mechanics, but also extend quantum mechanics in various ways. And I'll just mention the keyword of generalized probabilistic theories, or GPTs. And in the study of GPTs, we can certainly allow for physical theories which obey all the laws. And this is the fantastic and amazing thing about generalized probabilistic theories. They're probabilistic theories, probability is conserved, yet they're not necessarily, they don't have a realization as in Hilbert space. It's possible with a generalized probabilistic theory to have evolutions which are not unitary, yet which preserve probability. So that you often hear the statement made that unitarity is the only way to preserve probability theory. That's blatantly false. There exist these generalized probabilistic theories. They are toy models, but they exist, and they allow you to preserve probability and have operationally well-defined physical theories. Yet they are able to, they do or can in principle go beyond quantum mechanics. And an idea which I like very much is a generalized probabilistic theory that's built on local laboratories in which quantum mechanics is obeyed, but globally violations of quantum mechanics are allowed. So this idea of black hole complementarity resonates a lot with this line of investigation into generalized probabilistic theories. But that's really an aside, and we can sort of close that aside off now, and we return to the paper. Because I believe that in this paper they won't push this point of view very strongly. Therefore, we should ask, if Alice's quantum state persists behind the horizon and that state is also encoded in the outgoing Hawking radiation received by Bob, can Alice or Bob verify their cloning? So things would be really bad if, in principle, Alice and Bob could come together in the future and compare their quantum systems and see, aha, indeed, I managed to clone a quantum state. So what we're about to do here is see if that kind of verification process, if that's in principle possible. All right? Does there in principle exist a scenario where Alice and Bob could get together later in the future and confirm a cloning event? If so, then that would violate even extensions of quantum mechanics, because we would have violated quantum mechanics from within a local laboratory. So how could that work? Well, Alice throws this quantum information in the black hole. How are we ever going to check that that information got cloned? Well, Alice would have to come in after the quantum information theory. Alice is going to have to take one for the team and jump into the black hole. And Bob will have to wait outside and look at the radiation, decode the quantum state of Alice, and then also jump into the black hole. and then meet up with Alice inside the black hole, compare notes, and see whether or not they were able to carry out a cloning operation. So that's the scenario that would, in principle, right, you wouldn't want to do this in practice, in principle, confirm a cloning event. So once Alice falls through the horizon, she won't be able to compare notes with Bob if he stays outside the black hole. So to have any hope of verifying the cloning, Bob needs to remain outside until he has retrieved Alice's qubits from the Hawking radiation, then dive into the black hole, seeking confirmation that both he and Alice have high fidelity copies of Alice's original quantum state. However, as long as the black hole retains Alice's qubits long enough before re-emitting them, then we are unable to say, based on our current understanding of quantum gravity, whether Bob will succeed or not. As best we can tell, then, the black hole complementarity hypothesis seems to be self-consistent, provided the black hole retains quantum information for sufficiently long time. To analyze this thought experiment, so now we're going to try and put some numbers to these words, it is convenient to describe the Schwarzschild black hole using Preskill null coordinates u and v as depicted in figure 2. These coordinates are related to the Schwarzschild coordinates by these formula here. So it's probably just more convenient to take a look at the coordinate system with respect to u and v. So according to this coordinate system, it's sort of like a distorted, accelerated coordinate system. The u coordinate points at 45 degrees towards the left, and the v coordinate points at 45 degrees towards the right. And Alice and Bob initially are outside the horizon, which is occurring at a constant u. So there's a coordinate u, the horizon now, according to this coordinate transformation here, which is accelerating, u coordinate accelerates with time. The black hole horizon is a straight line according to this coordinate system. It's located at a constant value of u. And firstly, Alice jumps into the black hole with her message. The message stays inside the black hole, and the radiation is coming outside the black hole, right? And these two regions are causally disconnected, so the message is really inside the black hole as opposed to outside the black hole, and the radiation is outside. Bob collects the radiation, jumps in, and then tries to confirm that his decoding of the message is the same as Alice's state, which is inside the black hole. In terms of these coordinates, the black hole's event horizon is not only a constant value of u, but it's at u equals 0, and the curvature singularity occurs at uv equals 1. Therefore, if Bob crosses the horizon at v equals v Bob, which is this point here, the singularity, he reaches the singularity at u less than v minus 1 Bob. But if Alice falls freely, the proper time she experiences between crossing the horizon at v Alice and reaching u v Bob is this. So this is just the time it takes, where c is a numerical constant that depends on Alice's initial data, right? If she falls from rest at r equals infinity, and with the constant c is about 1 over e. In terms of the Schwarzschild time, Bob's fall into the black hole is delayed relative to Alice's by delta t, where the ratio of these two times is this exponential function there, and therefore the proper time between these two events is given by this function here. It's exponentially decreasing with respect to the delay between Alice and Bob's fall into the black hole. Thus, Alice's proper time t, Alice's order of the Planck time, or shorter if Bob's entry into the black hole is delayed by delta t equals rs log rs. And that way, where does that time scale come from? That's the time it takes Bob to decode, right? We went around and looked at how long it took for the radiation to get out, and we came up with this estimate of t is rs times log rs. So that's where that time comes from, and already that's pushed us to the Planck time. This conclusion does not change substantially even if Alice rides a rocket, as long as her proper acceleration is small in Planck units, so as long as she doesn't create a black hole and accelerating. So if Alice, after crossing the horizon, has less than a Planck time to communicate with Bob about the status of her qubits, if Alice, after crossing the horizon, has less than a Planck time to communicate with Bob about the status of her qubits, then she is required to send her message using super Planckian frequencies. So Planck time, really short, and she needs to get that information. She needs to compare notes with Bob's state. So Alice is there with her state, Bob's there with his state. They come together and they want to do that swap check to see either they're the same state or not. Then they're going to have to execute that in extraordinarily small time, namely in a Planck unit of time. And in order for that to be confirmed, they really have to do it faster than a Planck time. So it's super Planckian times. And therefore super Planckian frequencies. And with our incomplete understanding of strongly coupled quantum gravity, we lack the tools to analyze the emission, transmission, and reception of such signals. I mean, if you have to construct, execute such an operation in such a short time, then you're probably going to have to expend astronomical amounts of energy that would push you into the quantum gravitational regime anyway. On the other hand, if Alice's proper time were long compared to the Planck time, then in principle she could send her qubits to Bob, or send a record of her measurement outcomes, allowing Bob to verify the cloning, and the verification could be analyzed using controlled semi-classical approximations. We conclude, if verifiable cloning does not occur, then black hole must retain Alice's information for a Schwarzschild time interval blah. Delta T is Rs log Rs. The big omega notation here indicates that it's a lower bound on the information retention time for asymptotically large Rs, up to a multiplicative constant. This finding is just barely compatible, and that's very intriguing, when things just hold on the nose, with the information retention time estimated in section 4 and 5. We noted already in section 4 that it takes Schwarzschild time order Rs log Rs for the Hawking radiation to climb from the stretched horizon to Bob's detectors. If Bob waits at a position that is a proper distance Rs from the horizon. In principle though, so it takes this long to get from the stretched horizon to the Bob's detectors when Bob's hovering in a Planck unit above. In principle though, Bob's decoding sphere could be located at a height where the black hole's thermal atmosphere has a constant temperature independent of Rs. At this height, Bob's clock runs slower than Schwarzschild time by an order Rs. And the outgoing radiation propagates from the stretched horizon to Bob in unit time. From the requirement that cloning is unverifiable, we require that by Bob's clock it should take time order log Rs, or at least log Rs, for Alice's quantum information to reappear in the thermal atmosphere. This version of the no-cloning argument usefully differentiates between the time delay due to the climb from the stretched horizon and the time delay due to the thermalization of the stretched horizon. A serious weakness in the no-cloning argument is that we have assumed that once Alice's information is received by Bob, he can decode the information instantaneously. In fact, as emphasized in the previous section, Bob's decoding map is a complex quantum operation acting on a large number of qubits. One could plausibly argue that fundamental laws of physics prevent Bob from performing the decoding operation fast enough for cloning to be verified behind the horizon, no matter how quickly Alice's qubits become encoded in the Hawking radiation. Now that's a sort of weakened form of the black hole complementarity principle. It's one that I don't particularly like, but yeah, it's logically possible. Nevertheless, we find it intriguing that our estimate of the information retention time is of the same order as the no-cloning limit that can be inferred if we neglect Bob's decoding time. So now we come to the conclusion of this paper, and I will say a couple of words on this whole process. Conclusions. The purpose of this article is largely pedagogical. I mean, although it was largely pedagogical, it took us on an extraordinary journey through a large number of topics in quantum information theory and gravity. On the one hand, many physicists who are interested in quantum behavior of black holes are familiar with Dom Page's observations concerning the entanglement entropy of an evaporating black hole. On the other, most quantum information theorists know about the quantum capacity of the quantum erasure channel. Here we point out that by invoking the latter, we can refine and extend the former. We have tried to convey our main points without relying too much on information theoretic jargon, in the hope of reaching a broad audience among those who are intrigued by these issues. The essential tool that allows us to go further than Page is the theory of quantum error correction, which was developed after Page's article was written. In fact, there is a delicious irony at the core of our analysis. In section 3, we modeled the internal dynamics of the black hole with a randomly selected unitary transformation, presuming that black holes, though they do not destroy information, are nearly optimal thermalizers. They rapidly convert information to a form that is very difficult to access in practice. However, a random unitary is nearly optimal encoder that achieves the quantum capacity for the quantum erasure channel. The dynamics that conceals quantum information effectively in practice by encoding it in a highly non-local manner also at the same time protects the information from damage as a matter of principle. It is not fully realistic to model the internal dynamics with a random unitary transformation because typical unitary transformations can be generated only by quantum circuits by exponential size. However, in section 5 we invoked recent results concerning efficient approximate encoding circuits for quantum error correcting codes, indicating that plausible local dynamics really can thermalize quantum information quickly. We argued in section 6 that our estimate of black holes' information retention time is just barely compatible with the principle that black hole evaporation must not realize verifiable quantum coding. Finally, what, if anything, are the broader implications of our observations for the black hole information puzzle? We're not sure, but we find it intriguing that the encoder for a good error-correcting code need not necessarily be unitary. Perhaps then there could be an interesting middle ground between unitary black hole dynamics and full-blown information loss. Even if some of the information deposited in a black hole remains inaccessible forever, quantum information encoded in small subsystems might escape in the Hawking radiation with relatively little damage. One possible model is to suppose that at any given time the black hole system B' really consists of two parts: the accessible system B_ac, which we might suppose that log B_ac is the Bekenstein-Hawking entropy, and an inaccessible system B_gone, which has been lost forever. For the information to be revealed to Bob, we require that correlations are destroyed not just between the reference system N and B_ac, but rather between N and B', which is the combination of B_ac and B_gone. As the radiation leaks out, B_ac shrinks, but B_gone may grow, and there is a competition between these two effects. If R is radiated away, then effective dimension of the discarded system is not R, but rather R divided by B_gone. Alice's quantum information is revealed when this effective dimension becomes larger than N. Quantum information encoded in a sufficiently small subsystem eventually escapes if the qubits are emitted in the radiation faster than they are destroyed by the black hole's interior, but the rate of escape is suppressed to a degree that depends on the rate of destruction. Since the information loss once allowed tends to be highly infectious, it is difficult to formulate deformations of quantum mechanics that incorporate a small amount of information loss, yet are compatible with the low energy experimental constraints. So this is a sort of, this point here is a bit of a lack of imagination point. We can't think of a good deformation, doesn't mean it doesn't exist. In the scheme we have just outlined, when a pure quantum state undergoes gravitational collapse to form a black hole and then evaporates completely, some of the information encoded in the initial quantum state really is destroyed, but the information encoded in any sufficiently small subsystem survives nearly unscathed. It might be fruitful to investigate how easily this type of partial information loss can be reconciled with the experimental successes of quantum mechanics. So that's the end of the paper, and that's the conclusion, and you have seen in the past 9-10 videos a journey through this paper from the beginning, from a state of, say, very little prior knowledge about the content of the paper, through to this end phase where we have read and perhaps not verified all the details on account of the wide scope of this article. So I hope you've enjoyed this journey with me. This kind of way of reading papers, it's taken, I think, in real terms about 10-12 hours of real actual time to read the paper. This sort of molecular reading of a paper in this molecular detail is something that is good practice, and you should do occasionally with important papers that are important for your work, or that you are particularly interested in. However, I wouldn't recommend reading a paper at this level of detail, or I wouldn't recommend reading every paper that you're interested in at this level of detail. Really, you should meditate for quite a while before going ahead and investing such a large amount of time. I mean, we did it in 10 to 12 hours. This paper was conducive to about that time investment, but there are other papers where you could easily spend 100 hours trying to get all the details out of it and trying to understand all the aspects of it. So this way of reading an article is not to be undertaken lightly, in my opinion. I don't do this very often personally, and but when you do choose to read a paper in this kind of detail, then the rewards are proportionally great. You learn a whole bunch of new skills, and you gain a whole bunch of new ideas about what you could work on next. For now, I think we will stop our discussion of this paper. We could, with no difficulty at all, read this paper again, and we'd learn more things. We'd investigate more parenthetic remarks and learn new skills, and that will indeed be rewarding for many of you. But for this seminar, for purposes of this seminar, I will cease reading through the paper today, and thank you very much for your time, endurance, and attention. And until next time, goodbye.